everyone, and welcome back to the Infodump, the series where I take a deep, but not necessarily scholarly, dive into a particular topic. We are continuing, of course, with our first topic of physics, and I just want to apologize for not putting out an episode last week. Holidays have been happening, so stuff kind of got in the way, as it were. And as a result, not this week, but next week, I'm going to be putting out a sort of double feature for this and for the other stuff that I have missed a chance to actually probably, record two stuff for. Yeah. So, with that out of the way, let's just real quick do a little bit of a recap of what we talked about last week. Or, not last week. Last time, 2 weeks ago. And of course, since it has been 2 weeks, do forgive me if I miss any important stuff or if I go over stuff that I went over last week. But last week was about, really towards the end, atomic theory, which the reason I glossed over it so much is because I'm going to explain it more once I'm done with the sort of history subunit. And that is the same for what we're going to be talking about today. This is going to be mostly an overview of the most recent developments, plural, in, physics. And I don't mean most recent as in, super current. I mean most recent as in, the big world-changing theories. Now, the first one of these that you're probably thinking of is, of course, our boy Einstein and his theories of special and general relativity. Those are actually what I'm going to get to in a little bit. First, because we're trying to go in a vaguely chronological order, we're going to talk about quantum theory. Now, you've probably heard of stuff like Schrödinger's cat and quantum superposition. I mean, if you've ever consumed any sort of sci-fi media, you've probably seen the word quantum thrown around like a... I can't even think of a good metaphor right now. I guess like confetti at a birthday party. Because, it's the part of physics that we least understand. And therefore, whenever science fiction authors want to hand-wave their space magic or whatever, or their impossible technology, they will just say, quantum mechanics! And assume that the reader does not know enough about actual quantum mechanics to be able to make sense of it. Now, the earliest roots of quantum theory actually go way the heck back to the early experiments on how light works. Now, it has long been known that light functions as a wave. That is to say, the light that we see coming off of everything is essentially an energy wave in the electromagnetic spectrum, as well as heat, specifically radiated heat, not contact heat, and all sorts of radio, television, microwave, etc. That is in fact where the microwave in microwave comes from. It uses what's called microwave radiation. And before you start freaking out, radiation in a specifically scientific phrase is not specifically the kind that, is bad for you. That is specifically referred to as ionizing radiation. Although, you don't want to expose yourself to too many microwaves either, because, if it can cook your food, it can cook you. But it's not going to give you cancer or anything like that. That is what ionizing radiation does. Now, the main issue with light being treated as a wave is the fact that there was some experimental data that showed that maybe it wasn't a wave. Maybe it was a particle. And on top of that, if light is a wave, then what is it traveling through? Because, except for light, we have a known medium for all other sorts of waves. Waves, like physical waves, those go through matter. When you look at, things that are energy waves, it's usually in some form of energy current. And that was sort of the foundation of the understanding, but then the attempts at proving the what's called luminous aether, the sort of hypothetical physical material that light would be moving through, the medium that the wave would be traveling in, was just not there. The experiments attempting to prove it completely proved its non-existence. And so that, of course, drove support for the particle theory, but it didn't explain why the wave measurements made sense. So that started making a bit of a tricky conundrum. And that was just an ongoing debate for a really long time. Now, that's one part of this, one of the building blocks that we need to understand. The second building block is what's called the black body radiation problem. Essentially, the black body radiation problem is the quote-unquote bizarre specificity of radiation, specifically thermal radiation or heat radiation. So, when you have an object, it will emit light in the electromagnetic spectrum, but at a very low energy level, and that is what we perceive as heat. So, the idea being, a black body is something that is completely opaque, doesn't reflect any light, but it still emits heat. So that's sort of what the black body in the black body radiation is. Essentially, the idea behind the problem is it radiates in very specific sort of bands and groups, and there's a distinct order to it. And not only that, but it seems essentially like from this perspective, it seems like the light that is coming in is just being lost, and then thermal energy, this much lower energy light, is being emitted. So something is happening within the black body to reduce the energy of the light. And if it's just being completely lost, then that violates the law of conservation of energy. But if maybe something is happening to it, if that energy is being redirected somewhere else, then maybe that has something to do with it. But even then, what is it about that process that is causing everything to be so specific, for these specific bands of energy to be emitted? Well, this is where quantum theory comes in. If you're not familiar with the etymology of the word, the term quantum derives from the Latin quanta, essentially meaning how much, like an amount. So, that's the word where we get stuff like quantity, right? So, quantum theory is the idea that there's these specific amounts of energy that are sort of almost like units that everything is operating in. That there are these packets of energy, almost like packets of data when you're doing a data transfer. So there's these distinct packets with a certain amount of energy in them that are being sent, and that is what makes up these electromagnetic waves, this light. So it's the idea that what should be a wave is behaving like a particle, and what kind of is-ish a particle is a particle of pure energy, which is very hard for really anyone to wrap their heads around, working from, a reality-based, physical-based mindset, because it's not exactly accurate. It's mostly on the money, but it's not quite accurate. Now, the idea of quanta, the coining of the word quantum, that came around in 1900, right as the century turned into the 20th century. And it was coined by Max Planck, whose name comes up all the time, not because he was, super influential per se, he was certainly the father of quantum theory, but because the constant named for him, Planck's constant, is absolutely everywhere. It is one of what you could call the scaling constants, where it is what we need to use to get our macroscopic measurements to work on a quantum microscopic, well, more than microscopic, subatomic level. Now, he, of course, could not wrap his head around his own math, around his own research. And so he was pretty sure that he had figured out a shortcut, a trick, and that the real way was something that could be simplified down to that trick. But as it turns out, it's kind of the opposite. Planck figured out the way that things were actually working, and other ways of trying to measure it are simplified down from his equations. His little mathematical trick was the way things work. In fact, Einstein, yes, that Einstein, used the quantum hypothesis to create a solution for the question of the photoelectric effect, where shining light on certain materials creates an electrical current. Then, Niels Bohr used it to create a model of the hydrogen atom that shows the spectral lines, which is what we use in what's called a spectrograph. That's how we tell what's in different stars of hydrogen. So then, of course, we bounce things around. Einstein comes up with the idea of the photon, which is the actual particle of light. That is what that quantum of light is. And this essentially creates the old quantum theory, as it's called. It's the beginning of the realization that energy functions in discrete units, and that by understanding what is in these units, how much energy there is, we can understand what their effect will be, as well as the understanding particularly in terms of atoms, because again, this was, back in the days when the atom was the core of physics. The realization that when light hits an object and is not reflected, it is essentially imparting all of its energy into the electrons, which then, depending on the circumstances, will radiate out, will lose that energy over time. That is why, if you shine a light on something, not only will certain materials create electrical voltage, but also, if you shine a light on something that is completely black, this hypothetical black body, it will get hot, despite you not necessarily putting heat into it, except the negligible amount that's coming with the visible light, which again, should not be much. Certainly not as much as you're feeling. And that really was the realization that came from old quantum theory. Then came the more famous ones. Heisenberg, not Breaking Bad, Werner Heisenberg, the guy who created what we call the uncertainty principle, as well as Schrödinger. And with them came the concept and the field of quantum mechanics, the idea that you can study how these quanta of energy work, and from that, learn how the universe works at that level. Schrödinger, of course, famously came up with his thought experiment about the cat, but we will get more into the exact details around that later. Now, over time, quantum theory has been refined and enhanced and developed. We have a pretty good understanding of the quantum particles for most forms of energy. Or, more accurately, for most waves. Because not all waves are necessarily forms of energy. Because, well, gravity exists. And gravity is really weird. As far as we can tell, gravity was the first of what we call the fundamental forces to split off. We've discovered carrier particles, as they're called, for all the other fundamental forces. We've discovered particles for all the other forms of energy. We've got everything but gravity. And right now, our best way for understanding gravity is the second thing I want to talk about today, which is relativity. That's right, good old Einstein's relativity. So, essentially, Einsteinian relativity is a development on what I refer to as Galilean or classical or Newtonian relativity. This idea that came from Galileo that if you are standing on a boat, moving in a particular direction, and you throw a ball opposite to the direction the boat is moving, with the same, velocity, it will appear, or not velocity, same speed, opposite velocity, because speed is velocity just without regard to direction. Velocity cares about its direction. So if you throw a ball with the same speed as the boat but going in the opposite direction, it will look to you on the boat like it is moving off the back of the boat. But to someone standing on, say, a beach watching the boat go by from the side, the ball will just sort of stop in space and fall. It won't move backwards or anything like that. It'll just stop, fall. Now, Einstein built upon that earlier theory of relativity when he was very bored looking out the window of his Swiss patent office, and he noticed a carpenter on the roof of a nearby building, and he thought to himself, if that man fell, he would not be able to feel his own weight. Which then led to more thought experiments, and the gradual realization that acceleration is no different from gravity, which then, of course, led to him questioning what exactly gravity is. And we will get into this more when we talk specifically about relativity and go into it and all the stuff about it, rather than just this recap of the history. But essentially, he began with general relativity, which is essentially his theory of gravity. Now, what general relativity boils down to is that gravity isn't real. Not as a force, anyway. What it is an effect that high concentrations of energy or matter have to twist space and time. The idea being that, in keeping with Newtonian laws of motion, any object will, in fact, continue on a straight path, unless it is acted on by some outside force. But gravity isn't a force. What gravity does is twist space-time so that that straight path is not straight to us, the observer. In 4 dimensions, it is straight. But in 3, it is curved. And so, we, being incapable of perceiving the 4th dimension except by experiencing it, that 4th dimension being time, only see the curved 3-dimensional path. But with that 4th dimension, it is straight as an arrow. Like I said, Einstein's relativity is currently the best metric we have for understanding how gravity works and what it is. He followed it up with special relativity, which was sort of an attempt at a unified theory of everything that fell flat on its face because he couldn't reconcile it with quantum mechanics. Einstein famously had a strong disdain for the new quantum theory that we now consider quantum mechanics. He famously said, "God does not play dice with the universe." Now, of course, this does not necessarily mean that he had some sort of great understanding that all the proponents of quantum mechanics didn't. Quite the opposite. He just couldn't wrap his head around it. He did not want this fundamental randomness to be part of the universe. He wanted things to be deterministic. And unfortunately, that probably worked out for the theory of special relativity, or special theory of relativity, whichever one you want to call it. Because, well, we still haven't figured out quantum gravity. Not really. We've got theories of quantum gravity, that's true, but they don't work. Theories of quantum gravity break down where special relativity starts working, and special relativity starts working where quantum gravity breaks down. And general relativity sort of works in the middle. But even then, there's too many direct contradictions between the theories, and yet they are not compatible. Like, they are both experimentally true, but they're not compatible. So, until we have much better A, data, B, tools, and C, knowledge about quantum mechanics, we cannot really have a functional theory of quantum gravity. Which means that we can't have a unified theory of everything. The sort of holy grail, in a sense, of physics. This one theory that is the basis of all physical phenomena. And much of physics sort of history, if you will, after the development of the theories of relativity and of quantum theory has just been searching and searching and searching for quantum gravity, for the sole purpose of having that unified theory. We've found a whole lot of other stuff along the way. Stephen Hawking, of course, found black holes and Hawking radiation coming from them. We've had all sorts of huge insights into the fundamental way the world works, like the proof of the Higgs boson and therefore the Higgs field via the Large Hadron Collider. We have figured out all these sort of little nooks and crannies, all these holes in our understanding of the world where we have been able to slot something in and have it work. But we still don't really have quantum gravity. And every time we think we've picked up gravity waves or gravitons, which are the hypothetical force carrier for gravity, we end up either disappointed, confused, or just both. Because, well, we can't reconcile the existence of gravity waves with general relativity. But we also can't reconcile their absence with quantum theory. And we can't reconcile their difficulty to find with either of those. Because if you believe they're not out there, then whatever you find is not gravity waves. If you believe that they are out there, then no matter how difficult it is to find them, you're still going to keep looking. Now, I personally am very much of the belief that there is something out there. Maybe not a force carrier for gravity, but some latchkey, in a sense. Some thing that will tie it all together, that will solve the puzzle once and for all. But every time we think we've figured it out, we end up figuring something else out. The Higgs field gives us an explanation for why high concentrations of matter and energy twist space-time the way they do, but the Higgs boson certainly isn't a graviton. It's more like the Higgs field is the thing that keeps mass, that keeps matter from being able to travel at the speed of light, because it's weighing it down and slowing it down and inflicting all these sort of relativistic effects when you have high levels of speed. So it's sort of the thing that links together high levels of energy with relativistic gravity. But it doesn't explain where to connect that with, well, quantum gravity. And all of that is assuming that we even have a quantum gravity theory in the first place, that we managed to develop one, which we have yet to be able to actually really do. Every attempt we have made at quantum gravity since, well, the development of quantum theory has either been completely self-contradictory, completely incompatible with general relativity and therefore with experimental data, or impossible to experimentally test. And sure, maybe one of the impossible to test ones is in fact accurate. But if it is, that just means that we'll never have an answer, which is something that no physicist likes to accept. No scientist likes to accept. Because science, at its core, is about looking for and finding the answers. So, with all that said and done, this really concludes our history subunit. Starting next week with the double feature, I'll be going into depth in the order and the way that I think physics should be taught. Not necessarily in the way that is easiest to understand, starting with classical mechanics and then moving on to quantum mechanics, but instead starting from the hard stuff. Because that is the foundation, the layer upon which the easy stuff is built. And if you start with the easy stuff, you find it hard to understand the hard stuff, because the easy stuff makes sense. But if you start with the hard stuff, you understand where the connection is right from the get-go, and you don't have to try and break down your macroscopic understanding to get a sense for how things work on a subatomic scale. So, with that all said and done, thank you very much for watching and or listening, and I will see you all next time.